So, let me just I had pointed out in the last lecture that there was a little error in computing this number. So, I have just done the last two tableaus again. This is the inverse tableau presentation of the LPP algorithm for the parametric cost problem. So, the problem we were discussing in the last lecture, so that one continues here. So, the correction was somewhere here. So, just make sure with the tables in the last lecture you compare and see make the corrections wherever necessary. So, I think we had almost completed the problem. So, here in this case you see for the positive ones the ratios are 6 and okay, the 8 number is missing somewhere. This part we had done already and it was for x6. So, this should be okay, this number should have been 8. No, not this one. Achha, this I am showing you. Okay, this tableau shows you when x6 has been brought into the basis. So, this number was 48 and minus 6. Okay. So, when you take the ratio it will be minus 48 by 6 which would be 8. So, this tableau shows you the computation for the after x6 has been brought into the basis. So, you have the I mean okay. So, this you are pivoting on 2. Okay. So, this is for your basic column. So, anyway for x6 the ratio, the upper ratio would be 8 and the lower ratios are 6 for the mu, and you are pivoting on this. So, after this when you do the pivoting on 2, so you will be dividing by 2 and yeah. So, this tableau shows you after you have pivoted on this element. Okay. So, here in this case the interval was 6 and 8. So, the characteristic interval for the corresponding basis x5, x4 and x3, x5, x4 and x3 when these are the basic variables, the corresponding characteristic interval for mu is 6 comma 8, right. So, after and then x6 has to come into the basis. This is the pivoting element, you do the pivoting, you come back here and let us see what are the ratios. Yeah, I have computed them for you. 66 minus 66 upon 8. So, that becomes 66 upon 8 which is equal to 8.25. Okay. And for the negative ones, for the positive ones the ratios are 30 by 4 which will be 7.5 and 24 by 3 which is 8. So, you see this is your lower, because you take the max of this and there is only one entry here. So, that is only one, otherwise you would have more than one, you would have taken the minimum of the two whatever the entries here. So, therefore, the next characteristic interval is for you 8 and 8.25 as you would expect, right. This lower and this upper should match. Okay. Now, after 8.25 you see we can now make use of this fact that you started with your basis, your starting basis was x1, x2, x3. This was your starting basis. This was your starting basis. So, therefore, what figures here is your, this corresponds to x1 now. Okay. This whole column corresponds to x1 because you started with your column for x1 here, and after all the iterations. So, actually this shows you the column for x1, this shows you the column for x2 and this shows you the column for x3. Okay. And so, from here you can see that for lambda, for mu greater than 8.25, this will be a candidate for coming into the basis. Your column A1 will be a candidate for coming into the basis, but corresponding entries here are all less than 0. So, therefore, this mu greater than 8.25, x1 is to become a basic variable. Yeah, but y1 is all less than or equal to 0. In fact, it is all less than 0. So, this implies problem is unbounded for mu greater than or equal to 82.25 greater than, because it has to be an open interval, right. For 8.25 we already have a basis which is optimal, which is your x5, x4 and x6 are the basic variables, right. And okay, the starting tableau is not there, but you could have you could have checked that we started with, I think we started with the 6 up to, yeah. So, so far the characteristic intervals that you have obtained are this 8.25 8 and 8.25, and then you have the open interval 8.25 to infinity, right. And for mu less than 6, if you in the original tableau, your A4 was less than 0, less than or equal to 0, whatever it is. Oh, so that would, so this would imply original tableau A4 and C4 minus Z4 also less than 0. So this implies the problem is infeasible, oh sorry, unbounded again. The problem is unbounded again for mu less than 6. Okay. Is unbounded for mu less than 6. Right. So therefore, you have the complete partition for the, so partition of the partition of the real line is as follows. So this is minus infinity to 6 open interval, then 6 to 8 is a closed interval, 8 to 8.25 is again a characteristic interval which is closed, and then you have the open interval 8.25 to infinity. See, while showing you the breakup for the real line, we had computed all the intervals, but while writing out the final breakup for the real line, I should have written minus infinity 6, and then we had also computed this, which I did not mention in the lecture. So, this was a singleton, right, and then of course, we recorded all the other intervals, which is 8, 8.25 and finally 8.25 infinity. So, the real breakup, that means you, when you add up all these intervals, you would get the breakup for the real line from minus infinity to infinity. So, the singleton, the interval containing the single element 6 got left out. So, kindly read this as the real breakup of the real line. As occasion arises, we will also see that we may need such situations after we have solved a particular problem. So, this can we will be coming back to it sometime again. Okay. So, now I want to start a new topic, and that is, min cost, well, okay, the min is for short for minimize, min cost flow problem. And you will be surprised how vast the area is where the problems arise, which can be formulated, modeled as min cost flow problems. And then we will look at the special cases. I already looked at one of them. For example, when I formulate the general min cost flow problem, the shortest path problem that we discussed is also a special case, and I will show you later on how it is. But let me first, okay, so just a few terminologies, and then we can start defining and formulating the min cost flow problem. So, the idea is you have G is V and A. So, here again for the shortest path problem, I took the directed arcs, directed edges, which we call as arcs. So, G is V A, where V is the node set. So, I will just redefine, and A is the arc set, that is A is the pair, ordered pair, you can say I j ordered pairs. pairs for I and j belonging to V. So, that means you have a node I and you have a node j. The idea is you have a directed arc, that means you can go from I to j, this is the idea, and so this is the ordered pair I comma j. So, we also have concept of undirected edges which are called edges. So, edges where simply I and j, that means you can go from I to j or j to I, no direction is specified. Okay. And you can have a situation where you have some edges are directed and some edges are not directed. So, it will be called a mixed graph. So, anyway, usually when you have the direction set between all pairs of nodes, then you say that G is a directed graph, right. G is a directed graph when the edges are all directed. So, edges imply no direction when the edges are directed, are all when all the edges are directed, edges are directed. Okay, you can read it as directed. G is a directed, and another word for a directed graph is, another word is network. So, it is a network. So, network implies that there is direction from a node to another node. That means you are considering only, because networks are basically considered in the connection of flows, and so you always have directed edges in a network. So, I will be using directed graphs and networks synonymously, right. Sometimes I may refer to it as this and so on. So, some more so let me first define the thing, and let me define the problem. So, min cost problem, min cost flow problem can be formulated as okay, and I will define the terms as we go along. So, minimize z equal to summation Cij xij, where ij is your edge in the directed graph, subject to summation xij summation over j minus summation xki summation over k is equal to bi. I will define all these terms, and then we have an capacity constraint also. So, let me write this as less than or equal to uij, right, and here let me say that this is for each node. So, I belonging to V, that means for each node. So, yes, so let me specify the things. So, bi can be a positive or a negative number, right, and bi greater than 0 indicates the amount of a certain of a commodity of an item available. Okay, it could be the capacity. See, you may have telephone exchanges, and bi may denote the capacity of the phone calls that at a particular time the exchange can handle, right. As I said, in this course probably one cannot just give you all possible situations where these problems can occur, or where the problems can be formulated as a min cost flow problem, but hopefully you will get a good idea by the time we finish with the various special cases and so on of this class of problems. And of course, I will tell you why we are discussing it in the linear programming course, because as it is, you see, first of all, that the formulation is a linear programming problem, right, and then there will be many good other reasons for doing it here. Okay. So, let us see, bi positive indicates the amount of an item available at node I. Okay. Right. And Bi less than 0 would indicate the demand for the item at node I. Okay. So, obviously, what the concept is that positive quantity is available for supply and a negative number indicates that things are being demanded or required at that particular node, right. Then we refer to, so you, as you can guess that your Xij is the decision variable, right, decision variable, and it tells you decision variable regarding the amount to be sent along arc ij. Okay. So, you are using the arc ij. If you are using the arc ij, then Xij tells you, that means Xij positive value will tell you the amount that has to be sent on the arc ij, right. Then Uij is a positive number, Uij is positive and denotes the capacity of the capacity of arc ij. Yes, and you can immediately relate it to, say for example, if you are sending things by trucks, then the capacity of the truck, that there can there is a certain amount beyond which you cannot send the items through through the truck, or the railroad, you hire a carriage, that capacity, or telephone exchange, as I told you, for a particular arc, again the telephone lines are built for certain capacity. They cannot handle unlimited amount of volume of traffic. So, railroads and so on, all these situations you can figure out. So, Uij, so it is a very natural constraint on the system, on the variables, right. Fine. Then Cij, of course, is the cost. So, Cij is the cost of sending a unit of item on along arc ij. Okay. Finally, this gives you, these are your flow conservation constraints, which for remember for the shortest path problem, we wanted that see the Bi's were only 1 and -1 for the Bi was 1 for the node from which you wanted to begin your shortest path. It was -1 for the node which was to which the shortest path to be found, and then all other nodes were intermediate nodes, in the sense that they were only being used for the constructing the shortest path from the starting node to the ending node. So, they were all zeros. So, we have already sort of had a we have already looked at the flow conservation concept, and so here all it is saying is that from a particular node I, if Bi is positive, then Bi is the amount available at that node. So, certainly you do not want to be sending more than the item available at a node, and similarly at a demand node you would want the required amount to be sent to that point, right. While formulating this min cost max flow problem, I had in the beginning not mentioned that sigma Bi should be equal to 0. Later on I did say that, of course, this is the necessary condition, that all the Bi's must add up to 0. So, now I am just inserting it in the time beginning of the formulation of the problem. And as I told you that when arc leaving arc, so this was, yes, if an arc leaves a node, it has a positive sign. If an arc enters a node, it has a negative sign. So, it is possible that node I may be receiving some amount and then it is sending some amount, but the net amount, so whatever it receives, that is the amount beyond, say if this Bi is positive, right. What we are saying is that you may have some amount coming to node I, so that means the amount will become more than Bi. but then you will be sending amount to other nodes. So, finally, the conservation equation, the flow conservation equation says that the net amount that node I handles should not be more than B I, whether B I is positive or negative, right. Even if B I is negative, that means it will be receiving amount and it will be sending out, but the net amount. So, this tells you the total amount which is being sent from node I, and this tells you the amount which is coming from nodes like K to node I, right, and that is a minus thing. So, then the net amount that node I handles should be equal to B I, whether B I is positive or negative, right. So, these are the flow conservation equations. So, which we always maintain, and therefore, we maintain a feasible solution. Okay. Yes. So, now we need to have a few more definitions. Say, for example, I did define a path for you, but let us do it again in this course. So, first let us say that yes. So, let us define a path. A path from, say, from node I to node J, and this is a sequence of. So, this is a sequence of arcs, let us say I K1, K1, K2. So, you see consecutive arcs, or we can say adjacent arcs, I to K1, then K1 to K2, because that is the concept of a path, right. And similarly, from here it will be KL to J. So, finally, KL to J, right. Some people like to define arcs and nodes, but I want to keep it simple. So, you understand that from I to K1, then K1 to K2. So, the node part is quite clear. Okay, fine. Sequence of arcs. Then we say that path is simple if no node is repeated. Okay. So, path is simple, and that is important for us, because sometimes. So, that means you are not coming back to a node and then going out. So, let me give you example. So, let us just consider a directed graph. Okay. So, you have a directed graph here. So, for example, a simple path would be something like 1, 3, 3, 2. Yes, I should have said something more. Now that I am giving the example, I realize that well, I have said things like, so 1, 3, 3, 2. Then you can have 3, 4, okay, and then 4, 6. So, simple path from 1 to 6. Yeah, I should have said here sequence of arcs where, let me add here, where either Ki plus 1 or Ki plus 1 Ki belongs to A. It's little crowded, but I think you can read it. So, what I am saying is that it is not necessary, when I am giving you a sequence of arcs, it is not necessary that each of the arcs is in A, it can be either way. So, the concept of path is a little general here, because what we are saying here is, whereas for the shortest path, when we were looking at a path, it was directed path, okay, because we wanted to actually go from 1 to 6, and so, for example, it was 1, 2, 2, 4, 4, 6. So, we were trying to find out paths which had the same direction, all arcs had the same direction, but here path is a little more general, and we can take it to be. So, for example, 1, 3, then I am taking 3 2 3 4. Okay, that would not be correct. So this would not be correct. 2 3. Yeah. So this would not be 1 3 2 3 3 4. I would have to make it 2 3. Right. So writing an example helps. Yeah. So it will be 1 3 2 3, then 3 4. That is also not correct. So let me take it to be 1 2. Okay. So a simple path would be 1 2 2 3, then 3 4 I can take, and 4 to 6. Okay. So this is a simple path from 1 to 6. But if you so not simple path, but if you take the path let me say 1 3 and then 3 4 4 2, and then if I add 2 3. So you see 1 3 3 4 4 2 2 3. So now the node is being repeated, node 3 is repeated, and then I can go from 3 to 5 and 5 to 6. So the path is not simple, is not okay. This is not a simple path, because you are repeating a node, you are visiting a node again, whereas here I am not visiting a node again. 1 2 2 3, then 3 4 and 4 6. Okay, so no node is being repeated. So that's very important. Simple paths. Okay, so path is simple. Now in if okay, now I want to define a cycle, or some people call it a circuit. So cycle is a simple path in which the first and the last nodes are the same. Okay, so a cycle or a circuit is a simple path. So for example, here let me give you an example here. Yeah, it's very simple. 1 2 2 3 3 1. 1 2 2 3 3 1. This is a cycle, right? So there are so many of them. 1 2 2 4 4 5 5 3 3 1, any of them. So the last node and the first node are the same, then it's in a simple path it becomes a cycle. Okay. Then we also are interested in another configuration, and there are many more other things which we will not need right away. So if we need them again, whenever we need them, I'll try to define. But right now I just want to begin with the basic definition so that we can start with the algorithm. This is a tree. Okay, so now you have a cycle and you want to look at, okay, you can also have a definition called subnetwork or a subgraph. So a subgraph, which will mean that it is a subgraph. So you want to call it G prime. This will be V and A prime. That means it has the same node set as G, but the arc set may be a subset of this, where A prime is a subset of A. This is important. So it becomes a subnetwork. Then you also maybe sometimes right. So this is good enough for us. Fine, subnetwork or a subgraph. So now we want to say that tree or a spanning tree is a subgraph. So everything is being defined with respect to the original graph G, which is VA. So a spanning tree is a subgraph with no cycles. Okay. With no cycles. So, for example, here remember a subgraph has to has the same node set. So, we are wanting a subgraph, but with no cycles. So, that means here if you remove the edges which are or arcs which are making cycles, then so for example, I would remove this. This can be, and of course, these are not unique. There can be so many spanning graphs. So, let me if I remove this, then what happens? You have a yes, you have a cycle. So, if you remove this, okay, is a subgraph with no cycles. No, one more thing I should have defined. There is still a cycle here. So, this is not okay, right, because this would have been a cycle, but 2, 4 and 5, yes, this would be a spanning tree, but then another concept which I should have defined, and that is connectedness. So, let me talk about connectedness. I will keep that as it is right now, connectedness. So, right after a path, I should have defined this thing after a path, right. A graph is connected if there is a path, and remember, when I say a path, I mean a simple path. If there is a path between every pair of nodes, every pair of nodes of G. So, connectedness, that means I should be able to connect two nodes, any two nodes of the graph via a path. Okay. So, what I drew for you was a connected graph, but for example, if I have something like this, right, and I have a singleton here, you may have this, you may have this, does not matter, but still this graph is not connected, because I cannot in any way reach from 1 to 5 or 2 to from any node here to 5, right. So, this is not a connected graph. So, we want connectedness. So, therefore, what I have to say here is the definition is not complete. The definition has to be is a connected subgraph with no cycles, is a, so that is very important here, one has to add is a connected this is very important. So, a connected subgraph with no cycles is a spanning tree, okay, because I could have had, see here we had this edge, does not matter which direction it is, suppose you consider this, okay. Then if I had not written the word connected, I could have had something like this, I could have had a subgraph. So, there are to be no cycles. So, I will have this, then I could have 4, 6 and 5, yes, no cycles. So, this is a subgraph, because all the nodes are there, the 6 nodes are there and no cycles are present. So, that definition was not complete. I have to say that it is a connected subgraph with no cycles. So, what I drew for you here finally is a, so this was a tree, right. So, here you can see how many edges, arcs 2, 4 and 5, 6 edges. So, this is the important result which we will not prove, because one requires a little bit of more rigor. So, we will simply take it as it is, and we will use this thoroughly. It is, so what the claim is, if cardinality of V is n, then any spanning tree of G will have exactly n minus 1 arcs. By the way, what I am defining is all also valid for an undirected graph, right. So, this is a spanning tree will have exactly n minus 1 arcs if the cardinality of the node set is n. Okay. And using this, then we can do a lot of interesting things. And so, now let me just put in a few words why we are see, of course, as I told you, many situations can be modeled as min cost flow problems. That is one important reason why we look at them. And secondly, why I am looking at these problems in the linear programming course is that I want to demonstrate that if your problems have special structures, then simplex algorithm exploits them beautifully, and we will see how it simplifies the algorithm, because the problems have special structure. And why do I say problems have special structures? Because you see, the constraints are this kind, and while discussing the shortest path problem, I showed you that when you write the node arc incidence matrix, which will be the coefficient matrix here, when you have on this side you have nodes and you have arcs here, then every column will have only two non-zero entries, and they will be 1 and minus 1. So, this I had shown you in the while we were discussing the shortest path problem, and I talked about the node arc incidence matrix. So, this special structure really simplifies the simplex algorithm, and in fact, you can, the way I will solve problems for you, I will actually without bothering to show you, give you the tableau, and I do not need to, I will actually show the progress of the simplex algorithm on the graph itself, and you can see how things are happening. So, therefore, another aspect of, and that is why we said that linear programming is the simplex algorithm is so versatile that you do not need to keep on adding about talking about its properties. And as the course is unfolding, you see that you can really do many things with the simplex algorithm. And so, we'll define the concept of base and what a basic feasible solution here would mean, and so on. So, I will continue defining. Yeah, by the way, I should have said also that here very important condition is that sigma bi is 0. This is very important, that is, it is a balanced, because when I am saying flow conservation and I am saying that whatever is available should be also that since we have equality constraints, is very important, and we will show you why. Because if you sum up this thing with respect to I, then you see that this sum and this sum will be exactly the same, and so sigma bi must be 0. So, this is a necessary condition for feasibility of this problem. So, therefore, feasibility will also not be a concern here. We will discuss assignment 5 now with you, which is based on the portion of sensitivity analysis and parametric programming that we discussed in the last few lectures. So, the first problem is a product mix problem. That means, you are given some raw materials and the manufacturer has to manufacture certain products, and he has to maximize his profit. So, because we want to formulate the problem as a minimizing problem, so I have taken minus of the objective function, and so it is a minimization problem with minus cost coefficients, and then the raw materials available are there are 3 different raw materials, and the availability is given to you of these raw materials. Okay. And now, x5, x6 and x7 are the slack variables, and corresponding to the 3 inequalities. Then B is a optimal basis, and I have given you the corresponding. So, I have told you that the variables x1, x3 and x2 are the basic variables. Okay. That means, your basis will consist of columns A1, A3 and A2, and then I have given you the B inverse. Right now, you have to answer these following questions, which are concerned with post optimality analysis, and I would like you to support your answers with good proper reasons, right. So, for example, in the first part, in the part A, I am asking you to if you know that you can increase the availability of one of the raw materials, then which one will you choose? And you know that the person is trying to maximize his profit, the manufacturer, and the dual variables give you the prices of the raw materials. So therefore, you can now figure out how to answer this question. Okay. So what I am asking you is, you have a choice of increasing the availability of only one of the materials in by 1 unit. Which one will you choose? So the rate of increase of the objective function value is given by the dual variables. Okay. Part B says, what is an optimum feasible solution? What is an optimum solution if availability of B2 is increased by 31 units? Of course, optimal solution implies feasibility. If available of B2 is increased, so right hand side value of B2 has increased by 31 units, I want you to find out the optimal solution. Either the current solution is optimal, and if not, then you have to apply dual simplex algorithm. Okay. Part C asks you to find out if total of 10 units of third raw material can be made available, that is 4 units more, already 6 are available. So, 4 more are available. What is the maximum amount you can afford to pay for it? So, kindly think about it again, the answer will come through the dual variables. So, what is the maximum amount you can afford to pay for it? Part D says that obtain the interval for C1 such that the current solution remains optimal for all values of C1 in that interval, and do the same for C2. Okay, C1 and C2 both turn out to be optimal intervals. Okay, maybe you can also on your own do it for some non-basic variables also, the price ranging. Fine. Part E says that if XB denotes the number, X8 denotes the number of new product that the company has the option to produce at rupees 10 per unit. Oh no, it should have been minus rupee, because again see, because the objective function I am writing as minimization. So therefore, this should be actually minus 10 per unit. In the objective function, the cost coefficient will be right. Okay. So I have taken care of that in the problem. So the actual cost is 10, but the profit is 10 rupees per unit, but in the objective function it will appear as minus 10 x8, since we are minimizing the objective function. All right. So then let A8 transpose, I am giving you the column, this is parameterized, it has a parameter lambda appearing in it. So that means here we are considering changes in the technology coefficients, and what input output coefficients you can call, at what value of lambda will it become profitable to manufacture the new product. So this, remember, when you add a new product, that means you are adding a new column, you add a new constraint to the dual problem. So again you can try to answer what the value of lambda would be, for which or what it can be more than one value of lambda, for which the current solution will remain optimal. That means you have to actually check for dual feasibility. In F, you have to find out the range of values of theta for which the current solution will remain optimal if the input output coefficient A22 is changed to A22 plus theta. Again here I am trying to A22 corresponds to basic column, and therefore you will have to do a little bit of work to find out the range of range for theta, so that the current solution remains optimal. Problem 2. Now here you have a parametric right hand side problem, and this I have already discussed in my lecture, but I would like you to sit down and write it down properly. So you have to say that you have to answer the question that if the problem is infeasible for a particular value of lambda, which is lambda naught, then you have to show that the problem will either be infeasible for all lambda less than or equal to lambda naught, or for all values of lambda greater than or equal to lambda naught. I have been emphasizing for you that either infeasibility or unboundedness will always be valid for an open interval, and so I want you to prove it here. Question 3, I have designed specifically, I mean I took some time to come out with the right numbers. Of course, the calculations may still prove to be a little cumbersome, but anyway, in the third problem I have given you it is a parametric cost problem. Okay, so the C row is the top one, C star is the row below it, and it is a two constraint problem. So objective function is to be minimized. Solve the problem for all values of the parameter mu, starting with the basic feasible solution consisting of the basic variables x1, x5. That means your starting basis will consist of the columns A1 and A5. So, I wanted to actually design a problem in which and give you a basis for which there is no, which is not optimal for any value of mu. It was the idea, right? And so finally I could do it. And so in this you will see that when you come out with a basis, and when you compute the lower value for mu and upper value for mu, the lower value will be higher than the upper value. And so the interval, the characteristic interval is empty corresponding to this basis. Okay. And so now you have to proceed from here. And yes, what will be the idea here, that say the lower interval is bigger than the upper interval. So where will you begin? You will begin with the upper interval, because the corresponding, when the value is less than the upper interval value, say mu upper bar. So when value of mu is less than mu upper bar, your corresponding variable, the relative cost will become negative, and so you can proceed with the values of mu less than mu upper bar. From there you will begin, and then you will be able to, because see, it will not help you to choose the lower thing, since the lower mu lower bar is higher than the mu upper bar. So you should proceed with the mu upper bar, and so start with mu less than mu upper bar, and you should be able to continue and then get a full partition for the real line. Okay. So of course this is not the end of problems that you can work out on sensitivity analysis and parametric analysis. These are only representative problems, and I hope that you will try out many more on your own from many other textbooks. And I have already, the reference books I have already mentioned to you right in the beginning, and all these books have a lot of problems for you to work out and get a good feeling for the post optimality analysis that we have discussed so far. Okay.